Ready to go? Well, I would like to welcome everyone for our Water Lecture series. I think this is the second to last lecture of the semester. I would like to welcome our colleagues from MINDOT who made the trip from their office to attend the seminar. And it is my pleasure to introduce our speaker, Professor Andrew Braham, who is an associate professor at the University of Arkansas, but he is originally from Wisconsin. Actually, he's a native of Madison, Wisconsin. He did his BS, Bachelor, and Master's in Civil Engineering at University of Wisconsin-Madison. Then he took a break, went to work for the industry, for Koch Industries in asphalt materials. Then he went back and got a PhD at the very well-known University of Illinois at Urbana-Champaign with Professor Bill Butler. During that time, I had the pleasure of working with Andrew on a very extensive project on low-temperature cracking. Was a national pool fund study. The lead state was Minnesota Department of Transportation. And after his more than fair share of low-temperature studies, he went to China, to Southeast University in Nanjing, and as a postdoc for 2 years. And then he came back and teaching and doing research at University of Arkansas. And his main area of interest is pavement maintenance and rehabilitation with a special focus on asphalt paving emulsions, which is a very complex area, very innovative area in pavement engineering. With this, please welcome Andrew for our seminar.
Thank you. Thanks, Mihai. I appreciate it. Well, thank you all very much for coming. I appreciate it. Thank you, Mihai, for that nice introduction. I have to admit I was a little nervous at dinner last night. He was alluding to some things that may or may not be said during the introduction, but it was very nice. I appreciate that. As he mentioned, we're going to be talking about pavement maintenance and rehabilitation, specifically related to our roadway network. I would like to acknowledge Alice Warren Garden for this series. This is a phenomenal series, and I'm very honored to be here and a part of it, so thank you, Mihai, for thinking of me. And also Sadie Casillas, who's in the middle, and Erica Young. They're two of my fine graduate students, so pretty much all of the good things you see in this presentation came directly from their hard work. And then all this data couldn't be collected without my undergrad research assistants, because they're the ones who dry the aggregate, sieve the aggregate, batch the aggregate, make the samples, compact the samples, cut the samples, test the samples, and all of that hard work. So a big thank you to all these people. So as Mihai mentioned, I am from Wisconsin. And when I heard that I was going to Arkansas, I kind of started panicking because my geography is not very strong. So I figure being back here up north, just to get everyone oriented, we are currently in Minneapolis, which is in Minnesota. And Arkansas is directly south of us. And Fayetteville, Arkansas is up in the northwest corner of the state. And it is amazingly easy to get there from here. You simply go to 35, you turn left, and in Kansas City, you turn left on 49, and you'll get to Fayetteville. So all you need to do is take 2 lefts, and we know this because my sister-in-law lives here in Minneapolis. So when we come here, we have to take 2 rights, and that's it. So very easy to get to and from Fayetteville and Minneapolis. This is a picture of the University of Arkansas. This specifically is Old Main. It's one of the more historic buildings on our campus. It houses some of our administrators and classrooms. This is a picture of our library. University of Arkansas has one primary library and then just a couple of small secondary libraries. But for example, the College of Engineering library is housed within the main library. And so the University of Arkansas is in the SEC. And I thought that the Big Ten took football very seriously until I went down to the SEC. And think of your guys' hockey seriousness plus your football plus your basketball, add a little more, and that's the seriousness of football down in the SEC. But it's a great environment to go to the games. Not so much this year for Arkansas, but we're hoping that you start low with the new head coach and then move upward over time. And then finally, this is where I spend the vast majority of my waking hours. This is Bell Engineering Laboratory, which is where the civil engineering department is housed on our campus. So the University of Arkansas was founded in 1871. Last year we had almost 26,000 students enrolled. Of those students, about 55% were from the state of Arkansas, and only about 5.5% were from outside of the United States. So we really truly are a land-grant institution serving the state of Arkansas heavily. And we have just over 4,000 graduate students. We have 131 buildings on about a half square mile of land. And the old main picture that you saw on the previous slide, that building was completed in 1875. And I think one of the coolest things about the University of Arkansas is when you're walking around campus, you're walking on the names of every single graduate from the University of Arkansas. So there are literally miles of sidewalks with everyone's name on it. And it's really funny because you see people like laying down next to their name while people are taking pictures, and people take etchings and everything. But it's a really cool historic tradition that they have. And when I was interviewing on campus, my best friend's mom went to school at the University of Arkansas, and I thought, oh, I'll take a short walk and find her name. I found it within 30 seconds. Little did I realize how lucky I was just to happen to like step right out where her name was, because there are a lot of names. The civil engineering department specifically, we have 15 tenure or tenure track faculty, and we're currently looking for a transportation engineer on the systems side. We have 305 undergraduate students, approximately 60 graduate students, and in 2017 we had just over $2 million of research expenditures. So that kind of gives you an idea about our size. And I mentioned earlier Erica and Sadie. You can see them here working in the lab very hard, and I was very happy to see that they all have the correct PPE on, personal protective equipment. That's always a good thing. So when Mihai invited me to give this lecture, the first thing I did was to look at other lectures. And what better way to do that than with Dr. David Tim. He's a professor down at Auburn University. And I kind of realized, all of us road guys or gals, we always kind of start with the same topics. And that's about how many roads we have and how bad our roads are in condition and all of this, which you all know is true. But I thought, well, I need to make it a little more interesting then. So let's take a look at what Dr. Tim presented on February 19th of 2016. These were the states he found, or the countries he found, and the roadway mileage. So I went to the website he went to, which is the CIA website, and you can see this is the updated numbers from 2018. Very little movement except for China. And you can see that China has added over approximately 300,000 miles of roads in the past 2 years. Now, what I found interesting, however, was there is a subcategory here, and that's also expressways. And the ranking of expressways is much different, and you can see China by far and away has the most expressways out of the top 5 countries. Now, Jennifer, we're going to need your help because you can see there's no info on Brazil. So if you could just email that to us, we could fill that in. So this is the updated knowledge from Dr. Tim's lecture 2.5 years ago. And also I felt I'd be remiss if I didn't include the EU. I know the EU is not a country, but it's often considered kind of a collection of countries and somewhat of a homogeneous block. And you can see here the EU has over 6.5 million miles of roads. So this is kind of an update on where our roads are, and this gives you an idea of the scope of the number of roads we have. And a large amount of these are not in good condition. And this is where this concept of maintenance and rehabilitation comes into play. So this is a map of the United States and our highway system, and just our highways, so our state highways and our interstate highways, are estimated to be worth $1.75 trillion. So we have an incredible amount of money invested in our roads. And as I like talking to my undergraduate classes about, really our transportation system is the backbone of our economy. It's how we move goods and services. If necessary, it's how our military moves. It is how we take vacations. So there's all these different facets about why our transportation system is important, and it is worth so much. And I'm sure a lot of you have heard of the ASCE Report Card. This is another thing that pavement engineers always bring up because it really explains why we need more funding for research. And that is just traffic loss to congestion. We're estimated to lose $160 billion in time and fuel. And you can see that's up from $101 billion in 2013, but that estimate only had fuel. It didn't take into account time loss. Money lost to deficient payments is 112 billion US dollars, and that's due to repair and operating costs. So next time you're on a bus and you feel it like clunking along on the road, think about what that's doing to that bus, and think about the potential operation and maintenance associated with fixing those buses that are going over these roads. That's a portion of where this $112 billion comes from. And then ASCE estimates that we would need to invest approximately $420 billion in order to raise our road from a grade D to a grade A just in the United States. So currently we spend $92 billion. We're short only $328 billion. So after you guys graduate and get really high-paying jobs and donate to the University of Minnesota, you can then start writing checks for $328 billion to get our roadway network back up into business. And you can see number is going in the wrong direction. In 2013, according to David Tim, we were $170 billion short. So lots of roads. These roads are important, and we're not taking care of them like we need to. And this is where the pavement maintenance and rehabilitation comes in as a potential solution. I like taking a big picture view of things here, but what is the purpose of pavements? So when pavement engineers are thinking about our pavements and we're designing our pavements, what do we design them for? And regardless of the type, I'm going to focus on asphalt concrete pavements, but there's also a lot of very good Portland cement concrete pavements out there. But pavements must first of all provide a safe traveling surface. Whenever DOTs are looking at a section of roadway or reconfiguring a section of roadway, one of the first things they always think about is this section of roadway safe? And if it's not, how can we increase the safety? And a couple of ways that we can help increase safety is to provide a smooth road, provide a road that has surface friction, because when you think about it, all of our vehicles have very small contact areas with the pavement. It's just the bottom of our 4 tires and then that pavement surface. That's all we have, and that's all of what's preventing us from sliding off the road. Another important design feature is the drainage of water. Pavement engineers don't like water going down into our pavement structure. Pavement engineers really don't like water sitting in our pavement structure. So we want to make sure water either gets diverted away or diverted out of our pavement structure. And then finally, what people think about most often though, is we need the structural capacity. So when you have these very heavy trucks moving down our interstates, we want to make sure that those trucks are supported properly so that the water can drain, so that you have proper surface friction, and so it's a smooth and safe traveling surface. And as I mentioned, these are both important for asphalt concrete and Portland cement concrete, but we will focus on asphalt concrete pavements. And there are many different terms, so if you ever want to get a big excited crowd going, go to a pavements conference and start talking about what is the right term for asphalt concrete pavements, and you would get 5, 6, 7 different answers, and then animated conversations would start and everyone would be happy and go get some cold beverages. But some common names are flexible pavements, hot mix asphalt. More common now is warm mix asphalt. That's simply reduced production and construction temperatures of hot mix asphalt. You'll hear blacktop, asphalt, and then for those of you who like the European terminology, you hear bitumen over in Europe. But they all mean the same thing. They're asphalt binder, also known as asphalt cement, mixed with rocks, placed on the pavement surface and compacted. And the question we have is, we have all these roads, and actually this is a picture here of Arkansas Avenue, which is in Fayetteville, and you can see there's a little bit of distress in the right wheel path in that left-hand lane, and that's because you're approaching a stoplight. And as you approach a stoplight, cars slow down. As they slow down, that pavement has heavier loads on it because the loads aren't moving as quickly. And what's happening here is some of that asphalt binder is coming to the surface of the roadway. And that's a distress. And this will decrease the surface friction of the roadway because the coefficient of friction of that asphalt binder is very low. So what can we do to make roads like this last longer before we need to completely replace them, which is very expensive? So here are some common maintenance and rehabilitation techniques. We'll start with just surface treatments. So we mentioned that 3 of the 5 purposes of a pavement have to do with just the very, very top part of a pavement structure, where that tire is touching the pavement, for the smoothness, for the surface friction, and for the drainage. And if you put different surface treatments on there, you could put a fog seal, a chip seal or a scrub seal, slurry seals or microsurfacing. You could perform crack fills. You can also put overlays on top. So this is actually putting some additional asphalt concrete on top of your existing pavement layer. And this comes in the form of either an ultra-thin bonded overlay or a standard overlay. And then you can look at some structural mechanisms as well. So if you know your pavement isn't strong enough to hold these loads, what can you do with that in-place material? So you don't need to take all of your existing material, physically remove it, and then physically bring in all new material, which is very expensive, very time-consuming. There's a lot of emissions related with that. You can do some of these techniques: hot-in-place recycling, cold-in-place recycling, or full-depth reclamation. So there's a lot of tools we have in our toolbox, and I could talk for about an hour and a half about any one of these sub-bullets. But what we're doing is we're taking a little more global perspective, and then we're going to focus a little bit on some research we've done with cold-in-place recycling, or CIR. But I just wanted you to be aware of the different options that are out there. And when we look at these options on a bigger scale, you can see here that the maintenance portion of pavement maintenance and rehabilitation, as I mentioned, it tends to deal with just that surface. And those are the surface treatments, and some people include the overlays. But when you talk about the rehabilitation, that's more of the structural, but then some people also include the overlays. So again, if you're at that conference with a bunch of pavement engineers, you can ask the question, is a standard overlay a maintenance or a rehabilitation technique? And people will be off to the races talking about whether it's one or the other. And there's a lot of discussion about that in our community. But in general, this is kind of how we split up the maintenance and rehabilitation activities. And there are more out there, but these are kind of the big ones. It's probably 95% of what's placed out on our roads right now. And it's important to know which one of those we apply in which place. So a very common phrase we use is the right treatment at the right time on the right road. So if we talked about the treatments, now we talk about, well, what are the roads? What kind of conditions are they in? And we have a whole bunch of different types of cracking. So next time you guys walk outside, I encourage you to look down, which is what pavement engineers spend most of their time doing, and look at all the different types of cracks in the roadways. And then you can even contact MnDOT and ask, well, what are all these different types of cracks? Because chances are, any given section of road, you'll see at least 3 or 4 different types of cracking, because no one type of cracks are the same. And you can have fatigue, block, edge, longitudinal, reflection, or transverse cracking. There's a lot of patching and potholes that are out there. So this cracking, as the road continues to deteriorate, material starts coming up and you get big potholes. Then people come in, they throw in a bunch of stuff, and that stuff goes away in about 5 minutes. But that's the patching and the potholes. Trust me, we are working on trying to get better pothole material out there, but it's a work in progress. And then we have surface deformation, which is rutting and shoving. So this is when the pavement's physically deforming and moving underneath the wheel loads. When you're thinking about just surface defects, bleeding, that's the effect that we saw on Arkansas Avenue before, where that asphalt binder is coming to the surface. We have raveling and we have polished aggregates. And then there's a bunch of miscellaneous distresses out there, including water, bleeding, and pumping. So for all of you who enjoy your electronic devices, I encourage you to search. I had Google in here, but then I didn't want to promote Google particularly. You can use any search engine that you'd like. But if you search FHWA-HRT-13-092, the 2014 Pavement Distress Identification Manual will pop up as one of the first 2 search engines. And this talks about all of these distresses in a large amount of detail, and it includes photos that have examples of low, medium, and severe types of each one of these distresses. So it's a fantastic resource, and you can download it for free. I encourage you, if you're going to spend some time with friends this weekend, you can maybe show it to them to spread the knowledge about pavements. It's a great resource, so I encourage everyone to take a look at that. Now here's the tricky part, is we know we have these distresses, and we know we have these treatments that can fix distresses, but how on earth do we start matching these? And these next 2 slides are just going to be a very brief introduction to some of the possibilities, because there is no one way to do any sort of treatment of an existing roadway. But for example, for a fog seal, you can place a fog seal on a road that has either oxidation or raveling or extremely minor cracking. You can put chip seals on roads that have a little more oxidation, maybe a little more raveling, a little more cracking or polished aggregate. For slurry seals and microsurfacing, it's very similar to chip seals. There's some pros and cons to each one, which I won't get into right now. But also if you have rutting, you can put microsurfacing down, and that actually can fill ruts and provide some structural capacity. And then crack seals is obviously for cracking. And you can look at this road here. This is taken in Kansas City. You have some minor cracking. Now this looks horrible, but this is actually a very well prepped road for a chip seal. So if you remember, our very first slide was a chip seal asphalt emulsion being sprayed on a roadway. They did a very nice job of filling all the cracks here. They cleaned the surface, and then when they place that asphalt emulsion on top of that clean, cracked fill surface, you'll have nice adhesion, and those cracks won't move up through the chip seal as much. So this is a crack treatment here, which they did a very nice job of addressing all of that cracking. And then the pavement surface is very light colored, and that means it's been oxidized. So the asphalt binder has reacted with the oxygen in the air, and it's aged it. So instead of being sticky and cohesive, it's turned brittle and dry at the very surface. So that was all the maintenance. Now we're moving to the rehabilitation. So we're talking a little bit more about the structural capacity of roadways. So you can put the ultra-thin bonded overlays or the standard overlays on roads that have medium cracking, bleeding and raveling, or polished aggregates. HIR and CIR, this is where you're starting to get more into going down into the pavement material with your rehabilitation technique. So if you have the severe cracking in the potholes, if you have rutting or shoving, or you have significant surface defects, you're actually taking in-place material right now and remixing it. And as I mentioned, we're going to talk about cold-in-place recycling later on, so you'll be able to see some examples of that. And then finally, full-depth reclamation is very similar to CIR, but it goes even deeper. And so that can actually help take care of some water bleeding and pumping. And I was debating on whether or not to own up to where this picture was taken, but I figure if I give credit for good roads, I should also give credit for poor roads. But this is on Garland Avenue down in Fayetteville. It's less than a half a mile from campus. And every time I walk by here, a tear comes to my eye, because I know as pavement engineers, we can do a better job than this. And we should be doing a better job than this. But we all recognize that there's a lot of things out there that we can improve. Now, another fantastic resource is roadresource.org. And I just went through all those maintenance and rehabilitation techniques. I just went through all those distresses. And if you go to roadresource.org, this is a tremendous resource that has a lot of information about those distresses, and then it makes a lot of discussion about connecting those distresses to what sort of treatment you can use. And then there's a bunch of metric calculators where you can actually put in your pavement network. You can talk about what you could do, how much would it cost, how much money do you have, what interest rate are you looking at? Because when we look at roadways, we don't look at just today. We look at 5 years in the future, 10 years, 20 years, 50 years in the future. So we have to think about things like interest rates. But it's a great resource, and I encourage you to play around with it, perhaps over winter break. Now, as I mentioned, I just wanted to set the stage for one type. So I mentioned that I could talk for an hour, hour and a half about any one of those treatments. We're just going to focus on cold-in-place recycling, because I just wanted to give you a taste of one of the treatments with a little more detail, and a taste of when we talk about research in this area, what sort of research are we doing? And we're going to do that with cold-in-place recycling. But before I go on, does anyone have any questions? No? Okay, great. So this is a picture of a cold-in-place recycling train, and there are many different pieces of equipment here. So on the very far right side of the picture, or on the right side of the screen, you can see here are some trucks that are getting ready to back up to the full train. So when you're doing cold-in-place recycling, you have medium or slow-set asphalt emulsion, you may have asphalt foam, you may have lime, Portland cement, fly ash, or kiln dust additives. So there's all these different potential materials you have. But the last thing you want to do is stop that train from moving. So when you're about to run out of a material, a new truck pulls up, the old empty truck pulls out, and then the full truck just backs in, and the train can keep moving. So within this train, at the very far right-hand side, you have a truck ready to replace one of the trucks in this train. It looks like the first truck of the train probably has the asphalt emulsion. I would assume this second truck is either a water truck, it may be a dry additive truck, or additive in a slurry seal, or a slurry form. Then we'll go through all these pieces of equipment in more detail, but you have a milling machine, you have a crushing machine, you have a pug mill to mix all these materials together, and then you have a paver in the back, so you have a bad road in front, and then you have a brand new road in back. And this train is probably about a quarter-mile long, so it's quite a bit of distance. And what's happening here is they're taking about 3 to 6 inches of existing pavement and they're milling it, which basically is this machine with big teeth on it, and it just grinds the road up, and then you mix these additives in and you place a new road behind there. So it's a very nice system. And then once this new road pops out the back, we call it a semi-stabilized base course. So it's not quite as strong as hot mix asphalt. So if you go down into Mihai's lab, he has hundreds of samples of asphalt sitting around there. It's not quite that strong, but it's stronger than completely unbound material. So we call it semi-bound material. And it's not appropriate for those tires to ride on it, so you put something on top of the CIR. You either put an overlay, a chip seal, a slurry seal, some sort of surface course so you can drive over this new pavement layer that you have. So here's kind of a zoom in of the milling machine. So within this area in the middle, there's this big drum with teeth on it, and it rotates. And if you look on YouTube, there's some nice videos of that happening. It's a very fascinating system. But usually when it's running, you can't see it because the drum is completely enclosed on the road, mainly so pieces of road don't go flying out of the sides. And it all stays intact and in the same place. And after you've milled the road, you put it up and put it down through a screen and a crusher. And this makes sure you don't have any oversized particles. Because if you're milling 3 to 6 inches and then paving 3 to 6 inches behind there, you don't want a 3-inch chunk of road in there because that big chunk of road could really mess with the capacity. So all the oversized particles kind of get spit back out, put through a small crusher, and then they go back through the screen. Then you have your additive systems. So you always add water, regardless of what it is, because you design these in an optimal moisture content. Then you add either asphalt emulsion or asphalt foam, and those are the binding materials, so that's what holds this semi-bound material together. And then if you desire, you can add lime or cementitious materials, and this adds a little extra stiffness. It makes the road a little stronger and gives just a little more oomph to that semi-bound layer. And you can see here, this is all done in the pug mill. So down here, there's actually a pug mill. It's underneath the screening unit. Everything gets dropped down into here, and there's hoses that are going to those feed trucks, and everything gets mixed together in this pug mill as well. Continuing back, after it comes out of the pug mill, it gets either dropped onto the pavement, so you might need a pickup machine, or it gets just dumped directly into the paver, and then it gets paved out the back, and then you compact it. Because if you talk about flexible materials, the amount of air in that pavement layer is very important. So just like hot mix asphalt or warm mix asphalt, the amount of air in cold in place recycling is very important. So you need to compact it, and there's usually 2 different types of compactors. There's a pneumatic roller and a steel wheel roller. So this is a pneumatic roller, and you can see here there are 4 tires on the front, and in the back there would be 3 tires, and they're staggered. And that kind of kneads the material down a little bit, so it gets pushed down and it rises up a little in the middle, but then those staggered tires push it down where it had risen up. And this goes back and forth a couple times to compact your pavement surface. But then you want, before you put that surface course on top, you want a nice smooth layer, so you put a steel wheel roller after you have compacted it with a pneumatic tire roller. And this is an interior picture of that milling machine. So you have your distressed pavement, you have this milling machine. Now I just explained to you the CIR paving train. That was kind of the Rolls Royce of CIR paving trains. It had all the bells and whistles. You can also do it all in one single machine, which is what this image is of. And here it gets milled and you inject the asphalt emulsion and any additives at the same place. And then out the back comes a recycled CIR layer. So if you ever get out on a CIR job and you don't see all those pieces of equipment, they may have either combined some or using slightly different pieces of equipment, but at the end you get the same result. So some of the our research that we're doing at the University of Arkansas is looking at the mixed design procedure. So you have this existing road, and then you have this new road, which is semi-bound material, but how do we take existing material from the road and design that new road? And that's what that mixed design is, and we specifically focus on asphalt emulsion stabilized cold in place recycling. But as I mentioned before, you could also do asphalt foam, and in fact you can also just have Portland cement stabilized too. But we focus on asphalt emulsion. And the current mixed design procedures just look at coating and mixing. So that's the first stage. So how well does the wrap, the recycled asphalt pavement, or the material that was milled, how well does that get coated by the asphalt emulsion, because you want coated particles. And then you compact it and you make the final strength measurements. So those are the only two things that are being done now. And what we're thinking of doing and we're working on is including 3 more concepts in the mixed design, and that's workability, compactibility, and cohesion gain. Now, before I go too much further, I want to make sure everyone knows what an asphalt emulsion is. Who's heard of an asphalt emulsion before stepping into this room? Okay, so a fair amount of people. That's good. I'm happy to see that. I'm always glad to tell more people about asphalt emulsion. But this is a nice little schematic of asphalt emulsion here. But what an asphalt emulsion is it's droplets of one liquid, the asphalt binder, in a second liquid, which is water. And you can see here the droplets are not soluble, which means that you can't mix it. It's not like putting salt in water where if you stir it, it mixes together. You cannot physically mix an oil and a liquid, or an asphalt binder and a water. Well, an oil and a water, or an asphalt binder and a water. So they're not soluble or insoluble. And you can see here on the edges of all of these little black spheres are small little emulsifier particles. And those are chemicals, and their tails bury down into the asphalt binder droplet, and their heads have a charge on them. And those charges can be positive or negative, but if they're the same charge, it's like 2 magnets of the same charge, they repel when they get close to each other, and that's what allows these asphalt emulsions to stay in suspension. So it's a very nice system. And it seems relatively straightforward, but you would not believe the problems that we can have with asphalt emulsion. So it's a very exciting field to be in, and I think Mihai was right. I think there's a lot that we don't know about this, and there's a lot of opportunities for more work to be done. And what happens, the way that asphalt emulsions work is because you have these asphalt binder droplets suspended in water, you can apply asphalt emulsions at ambient temperatures or at room temperatures. You don't need to heat everything up. So if you go out to a hot mix asphalt job site, everything is at 300 degrees Fahrenheit. 300 degrees Fahrenheit is very hot. Not only is there safety issues potentially with that because of burns, but also there's cost issues with all that heating, and there's emissions to heat all of that material up to those very high temperatures. So this is all done at ambient temperatures. So what we depend on with asphalt emulsions is to remove that water from the asphalt emulsion, and all that's left is the asphalt binder. So you get the same result at the end, it's just a different way of delivering the asphalt binder. And when we remove that water, we call that emulsion curing or breaking. So an asphalt emulsion can cure or an asphalt emulsion can break. And those both mean the same thing. The water is leaving the system. And I also just want to spend a couple minutes talking about what is a mixed design, since my whole presentation is talking about enhancing the mixed design of CIR. When we think about what is in cold in place recycling, we want to have all the proper material, but especially in the proper ratios. So we want to make sure we have enough of each material. So we want to make sure we have enough asphalt emulsion. We want to make sure we have enough of the milled material. And I mentioned this before, but the milled material is often called RAP, or recycled asphalt pavement, or reclaimed asphalt pavement. You'll see that as well. You want to make sure you have enough water, and then if you have any additives, you want to make sure you have enough of those as well. So the mixed design consists of taking all these different components, and it's kind of like cooking. You put them together, and you mix them, and hopefully, if you've done everything right, you'll have a very nice CIR product. Unlike me, when I try and make a cake, for example, it never seems to work out. That's because my mix design is off when I'm in the kitchen. So then I just go to a bakery and buy one, and I'm very happy. And having the optimal proportions of all these materials ensures that you have a high-performing CIR layer, because nothing discourages academics or government agency workers or the traveling public to have a brand new road placed down and it fails in 6 months. That is a great way to start getting people writing you letters about how you don't know how they do your job. So you want to make sure you have a high performance layer. So our current mix design, for those of you who are fans of specifications, they are a little bit of dry reading. You know, it's not quite as good as a John Grisham novel, but they are packed with very, very good information. So if you look at either AASHTO PP86 or AASHTO MP31, you'll see the existing cold-in-place recycling specifications. And this is what we use when we specify for an agency to use a CIR product. They will look to this and they will design that roadway around these two specifications. And the first one is essentially selecting the mixture components. So you want to make sure that you have enough asphalt emulsion and the proper size and proper quantity of recycled asphalt pavement or wrap. And then you want to make sure that that asphalt emulsion coats the wrap. So you have a nice even coating around your wrap material so it sticks together in the field. And as I mentioned, the second portion of existing mix designs is our final strength and stability. And this gives you an idea of the performance of the fully cured or fully broken mixture. So this is after all the water has left the system, you have a nice semi-stabilized layer, and you want to know what are the properties of that final stabilized layer. However, we think there's a little bit of stuff going on between those two steps. And the way that we've broken it down is into 3 additional components. So we still want to select our mixture components. That's still number 1. And the final one is still our final strength and stability. These are very important things. But we propose putting 3 steps in between these 2. Specifically, workability, which is the second step. And this talks about how we mix and place the asphalt emulsion with the wrap and the water and any of the additives. The compactibility, that talks about the densification. So as that pneumatic roller goes over and the steel wheel roller goes over, what's going on with the compactibility. And then the cohesion gain. Because after those rollers leave, there's still some water in that CIR layer. The asphalt emulsion is not fully broken. If you're compacting when the asphalt emulsion is fully broken, you're wasting your time because you're not going to get any more compaction because that water provides a lubrication for your compacting, which makes the air voids go down and to get a more dense material. So after you're done compacting, there still is some cohesion gain. And water's still leaving the system, so you still have some curing, and the stiffness starts increasing of that CIR layer. Once all of the water is gone, then we start looking at this final step, the final strength and stability. So Sadie, who is one of the grad students who helped put this together, this is her dissertation research that she's doing now, is looking at the workability, the compactibility, and the cohesion gain. So how are we going to do this? Or I should say more accurately, how is Sadie going to do this? Well, the first thing is we do want to develop enhanced CIR specifications. Remember, we're keeping the existing ones. We're just inputting 3 new steps in between the existing ones. And we want to include workability, compactibility, and cohesion gain. And we believe that when the asphalt emulsion breaks, when that water is leaving the system, there's some very complicated things going on. And I don't think we fully capture them right now, and I'm not sure we fully understand them right now. So we believe that between that mix design and the final strength, there's these stages that the CIR goes through as the asphalt emulsion is breaking, and it behaves differently at each one of those stages. And this will account, hopefully, for the breaking of the asphalt emulsion. So we have our 3 properties here. We have our workability, we have our compactibility, and we have our cohesion gain. And for the first phase of Sadie's research, she is doing some evaluation of material properties. So you can see here, there's the SGC compaction metrics. SGC stands for Superpave Gyratory Compactor, and we'll go over that in a minute. We have the Dongray Workability Test, or DWT. Then we have the Triaxial test. So all of you fans of soil and soil mechanics, you're going to get excited when we talk about the triaxial test. Then for the compactibility, we have the DWT again and the compaction metrics. And then for the cohesion, we have the direct shear test, the triaxial test on compacted material, and then also the raveling test. And I'm going to go over each one of these tests very briefly before showing some results. So this is the research component, but if I went to MnDOT and said, these are all the tests you need to run for CIR, they would say, that's great, but chances are we're not going to implement all those tests. It's just way too many. It takes a lot of time, it takes a lot of effort to run all these tests, and when you look at the amount of roads that we need to work with, there just aren't enough resources to do all of that. So our anticipated specifications are going to run off of these SGC compaction metrics and the direct shear test. Because the very nice thing is, whenever you make an asphalt concrete, a warm mix asphalt, a CIR sample, and a gyratory compactor, every single one of those samples you can get these compaction metrics off of with absolutely no additional work. It's just a little more data analysis, but no additional samples are needed. And then the direct shear test is a very quick test as well that can be run on any type of load frame. So this is using existing equipment that most contractors and all agencies have with a relatively reduced workload. It's one of the difficulties about being in pavements is that there are so many very technical challenges that we face, but at the end of the day, we do want to make sure that agencies can implement these. And while the state may have a lot of resources, when you start going down to a county and a city level, it's always difficult to make sure that everyone has the resources in order to get the data we need. And as I mentioned, we're currently in phase 1. So if I'm lucky enough to be invited back in 2 or 3 years, maybe I can show you phase 2 results. And then I can show a picture of myself on the third slide instead of Dr. Tim. So what is the Superpave gyratory compactor? Again, this is going to be used in the workability and compactibility component of the research. And what we do is we apply 600 kilopascals of compression on a confined CIR sample. I'll show a picture of a mold in a second, but it's basically a steel mold with a plate on top and bottom, and we push down on it with 600 kilopascals of pressure. As we're pushing down on it, the mold is actually at a 1.24 degree angle, and it is calibrated to 1.24 degrees, and it rotates a little bit. So it kind of rocks. It's a kneading action that's meant to simulate what happens in the field. So as you're pushing down and as it needs, it rotates, and every rotation is called a gyration. And you can imagine as you push down on the sample, the density is going up, or the amount of air in the sample is going down, so we get these compaction curves. And each gyration, you get a little denser material until eventually you've squeezed all the air out. And these density versus gyration plots are what provides the Superpave gyratory compaction metrics. Now the DWT also looks at workability and compactibility. So this is a picture of one of those molds. So you put material in that mold, you push down on it at 600 kilopascals, and this is what pops out. This is called an asphalt puck or an asphalt pill. For the DWT, however, you change the stress that's applied to the gyratory compactor. And you change it to 2 different levels. You change it from 600 to both 650 and 550, and then you record the strains that are being applied. And you guys ready for the only equation in my presentation? There it is. So I'm not really big into complicated equations. There's a lot of people in this room who are much better at equations than I am. But this is the equation that we have for this. So it's just the difference of the stresses over the difference of the strains. And that gives us an idea of what we call the workability or the DWT measurements. For the triaxial test, we're looking at both loose and compacted mixtures. So the workability is when it's loose. So basically we have our triaxial cell and we put loose material in there. We put our confining pressures on it. We have our axial and radial forces on there, and we can measure how it behaves as you change and apply those stresses on the tops and on the sides. And then when we compact it, we run the test again, and that gives an idea of how cohesive it is. How well is it sticking together? And the reason that we're running the triaxial test is we believe that this is a good test to capture actual fundamental properties of the material. So we're going to get both the cohesion and the friction angle off of that. And if we can correlate the cohesion and the friction angle from the triaxial test to the compaction metrics, and we get a good correlation, then we're able to develop specifications on the compaction metrics that have been backed up with a little more robust, a little more fundamental testing. So the point of the triaxial test in our research is to validate results from the compaction metrics, the DWT, and the direct shear test. So we don't have to put in specifications to run triaxial tests when doing a CIR mix design, because many labs, especially the smaller agencies or smaller contractors, they simply don't have this equipment. So it's not fair to ask them to run tests on equipment they don't have. The next test that we're looking at is the direct shear test, and this is measuring cohesion. And it is a guillotine type test, so this is looking at it from the side, and if you go into the screen, there are two metal confining plates, and you simply shear those two plates. And obviously, as the cohesion goes up, they're harder to shear. So as that asphalt emulsion continues to break, and as that water leaves the system, there's less lubrication for that material to move against itself, so in theory, the cohesion should go up. And we're trying to capture that with the direct shear test. And it's very easy to run these tests. You can run a lot of tests in a very short period of time. All you need is a simple load frame and these two jigs, one on each side, and you can run the direct shear test. So very, very quick, very efficient. This is one way to capture a cohesion test, but there is a specific test that's been used in cold in place recycling, and that's called the raveling test. Again, not everyone has the equipment for the raveling test, but we want to include it in our research because it allows us to compare data we're collecting now to other projects that have been performed that have used data from the raveling test. So I will discuss the raveling test a little bit. The raveling test is a measure of cohesion. You run it using ASTM D7196. And what you do is you place your cold in place recycling sample into this little round bin at the bottom. And then there's a hose on this metal portion on top, and you rotate it over the sample. So it's kind of an abrasion test of sorts. And you're dragging that hose across the surface of the sample, and you can imagine that starts pulling material off because of the friction between the hose and the surface of the material. And you can relate that to cohesion. So as the material dislodges, that's called raveling, and you can record how much material is lost due to that raveling. So there's a lot of data out there. If you use your search engine to look cold in place recycling raveling, a bunch of journal publications will probably pop up. So it's helpful for us to collect data here to compare it to those publications. So the workability, the compactibility, and cohesion are very dependent on the type of aggregate you're using and the asphalt emulsion. So I asked Mihai if I could talk for 3.5 hours. He said I couldn't. I would love to talk about this for 3.5 hours. I could talk all day. But because of the time, we're just going to look at the compactibility. So we've done a lot of work with the workability. We've done a lot of work with the cohesion. We're just going to look at the compactibility for the sake of this lecture. And if you're interested, I'd be more than happy to talk afterwards about the other portions as well. So with the compactibility, we're looking at the SGC compaction metrics, the Superpave Gyratory compaction metrics. And there's 3 metrics that we look at. The first is the number of gyrations to reach 76% density. So I mentioned that you put your material in the mold, you push down on it, you tilt it, and then that tilted mold rotates. And every gyration is recorded, and when it reaches 76% density, or there's 76% CIR material and 24% air, that is the number of gyration required to reach 76% density. Another compaction metric we're looking at is the Gyratory Compactibility Index, or GCI, and this is simply the ratio of the number of gyrations to at 20. What is the height at, oh, and there's a mistake on there, I apologize. What is the height at n equals 20, and what is the height at n equals 10? And you take the ratio of that to get the Gyratory Compaction Index. And this is very important that we're using this curve of the compaction, because based on the different type of emulsion you're using, based on the material you have, based on a whole host of other factors, the shape of this curve as the height goes down, as your gyrations go up, that shape can change. So something may be easier to compact at the very beginning and harder to compact later, and the GCI can capture that because it's looking at a range of that compaction curve. And then finally, the construction densification index, again, it's looking at the density versus gyration curve, and it's looking at the area under 8 gyrations to where you get 76% density. So this is the density that we're expecting to be obtained during the construction phase of the CIR construction. But again, it's very important to note that we're looking at the shape of this curve, because just looking at a point will only tell you one data point of information, just a picture in time. But by looking at the shape of the curve, we're able to see how that asphalt emulsion may be breaking or changing as those gyrations continue to increase. So I think there's a lot of exciting things that can be found from looking at the entire curve. And again, this is data that you're collecting when you're making every single sample. So there's no additional samples that are needed. You simply need to take that data, save it, and then put it through a spreadsheet. So I'm going to just show a little bit of data from these 3 compaction metrics, and then we'll wrap it up. So here you can see the number of gyrations to 76% density. What we did here, and this is actually some data that Erica collected, is we looked at 2 different emulsions. We looked at a proprietary emulsion, and we looked at a commodity emulsion. So if you go look in the yellow pages, I really doubt that anyone looks in the yellow pages very much anymore, but before the internet, we looked at the yellow pages. If you looked in the yellow pages for asphalt emulsion, they would probably say, well, we have 2 asphalt emulsions that you can use. You can use kind of the vanilla asphalt emulsion, it does a great job, or for just a little bit more, you can use our proprietary asphalt emulsion, which will do all these great things. So we're looking at these 2 different asphalt emulsions, one of which is, in theory, better performing. So the proprietary is the blue bars, and the commodity is the white bars. And then we looked at 3 different types of aggregate. 1 was from the field, and 2 were produced in the lab. The field wrap here, this was milled off an actual roadway. I think it was College Avenue in Northwest Arkansas. And it used a limestone aggregate. So in the lab, we simulated making that limestone aggregate wrap in the laboratory, and then we also switched the wrap to a syenite. So limestone and a syenite aggregates have very different properties. They have different charges, they have different chemical compositions, and when you think about asphalt emulsions, with those emulsifiers surrounding each droplet, the properties of that aggregate is very important and can change what type of asphalt emulsion you may use. So here, it appears that the proprietary asphalt emulsion takes longer to compact. So the number of gyrations to get to 76% density is higher for the proprietary emulsions. And in the syenite wrap, it's actually statistically significant. The other 2, there's some overlaps. So it takes longer, which could mean one of 2 things. 1, it could mean it's not statistically significant, or 2, it could indicate that we're still in the workability stage at N76. That asphalt emulsion is still providing that lubrication in order to compact the samples, and the commodity asphalt emulsion is doing that more than the proprietary. So that's kind of one finding that could be taken from here. The second one is the Gyratory Compactibility Index. The thing that popped out at me most is if you look at the limestone lab wrap and the field wrap, which also uses limestone, so these have the same 2 aggregate sources, they're switched. So here, the N76, the limestone lab wrap, has higher numbers than the field wrap, and here they have lower numbers. So it's not behaving the same as the lab-produced limestone. So what's coming out of the field is not behaving the same as what's happening in the lab. And this set off 2 flags. 1, it means that something's going on, and we're not quite sure what that is yet. But 2, it means what we're making in the lab is not representative of what's in the field. And that's kind of scary because we're trying to mimic what's happening in the field. Now, it's scary in a way, but it's also very exciting. It means that there's more that we can look into, that we really need to continue looking at these different metrics to figure out what's going on. And then finally here, you can see the limestone wrap again is lower than the field wrap. The syenite wrap is in the middle. And we're believing here that the shape of the compaction curve is playing a role because the limestone and the field wrap sources are again flipped from the N76. The N76 is just one point in time. The GCI and the CDI are over a range. So we feel that that shape is playing an effect. So this could again be workability, but there's a lot of things that we can be looking at. So as I mentioned, that was just a brief overlook of the data. If you're interested in hearing more about it, I'd love to talk about it afterwards. But we do believe that asphalt emulsion-based mixtures behave much differently than traditional asphalt concrete mixtures. To date, a lot of people have tried to take the same tests and the same methods for hot mix and just apply them directly to asphalt emulsion. We found out a lot of good things, but I think that we're simplifying a little too much, and we think that the breaking of the asphalt emulsion is the key. We think that the mix design for CIR needs to be more than just the mix design and the final strength, and we propose putting in workability, compactibility, and cohesion. We feel that these compaction metrics of what I showed, we also have some initial conclusions from the workability and the cohesion, but we feel that the compaction metrics may be capturing more than just the compaction portion of those 3 new steps. We think it is bleeding into that workability. So as we develop our specifications for workability, compactibility, and cohesion, separating the compactibility and the workability we think will be key. And we see similar trends that we saw for the compaction metrics in the workability and cohesion, but I won't go over all those numbers. So from an academic standpoint, from a research standpoint, this is exciting because we feel like there's a lot that we don't understand, and I would be remiss to my profession if I didn't say that more research is needed. That's how every single academic presentation ends, and in this case, though, it really is true, and I'm really looking forward to seeing what happens in phase 2. So a final picture here. This is another CIR project that we did in Claremore, Oklahoma. And you can see that train is a lot shorter, but it's a different piece of equipment. So whenever you go out on the job, you never know quite what you're going to see, but it's always interesting to see something new. So with that, I'd be happy to take any questions.
We have time for a few questions, and I'll have to bring the microphone to you. Okay, one question there.
What are the advantages or disadvantages to cold in place versus hot in place recycling?
Well, that's a great question. So the question is, what are the advantages of cold in place versus hot in place recycling? So hot in place recycling, it's really fascinating to see because there are 4 to 5 heaters. So they're like giant hair dryers that are 12 feet wide and about 20 feet long, and they pass very slowly over the pavement, and it heats the pavement surface. After that pavement surface has been heating, 1 to 3 inches gets milled up, usually rejuvenating agents placed in there, and then it's laid behind them. So there's a couple things that are different from CIR. If you recall, CIR is 3 to 6 inches deep, so it's a little deeper. And with CIR, you're not activating that asphalt binder, because when you heat up asphalt binder, it becomes sticky again. It becomes cohesive again. So in HIR, when you heat it, you can add chemicals that can actually chemically change that asphalt binder, and that's very difficult to do if you don't heat the rock. So I would say that the 2 biggest things are you can't change the properties of the asphalt binder as well with CIR, but you can go deeper with CIR. That's a good question. Thank you.
Another question?
I noticed that the compactibility and workability are quite similar concepts.
Mm-hmm.
So what is the real differences between those 2 concepts?
Right. Thank you. So the question is, what is the difference between the workability and the compactibility? And I think that's a great question, and this is something that we struggled with a lot. We believe that there are a couple important phases of a CIR paving operation. One is physically milling the material and mixing it, and then making sure it can get placed. And during those steps, you need to be able to continue to move the material around, and you don't want it to get stiff. And you want to be able to move it all the way until it comes out of the back of the paver, and then you physically start compacting it. So once you start compacting it, you're no longer trying to mix it, you're just increasing the density. And a lot of these proprietary emulsions say that it can be workable for a longer period. So if for some reason that paver is further behind than it should be, it can still pick the material up and easily place it behind there. But then another benefit is a lot of these emulsions say that you can return it to traffic more quickly, which means the water leaves the system very quickly, and that you don't want to have happen before that compaction. So I would say there's probably some gray area and perhaps a little bit of overlap, but we feel that getting it into the paver is a little different than when it's out of the paver and actually densifying. But that's something that it's always good to try and get a better grip on in our head.
Yes, one last question.
Very nice presentation, Andrew.
Thank you.
I was curious. The difference between the lab and the field were very significant. I was curious, the lab wrap, did you get it from coarse crushed in the lab or from the milled asphalt? And then the second question is, how do you envision that this matrix that you provide in the mix design will be met in the field?
Okay, so I'll take the first question first, and I might forget the second question before I finish answering the first one. But the first one is, we noticed a difference between the field limestone wrap and the lab-produced limestone wrap. And what we did is we actually took virgin limestone and we coated it with asphalt emulsion and crushed it. But then we also took crushed limestone and coated it, and we blended those. And it was a 75-25% blend. And we matched it by a grayscale analysis. So we took the field wrap and we ran a grayscale analysis on that. And then we blended the pre-crushed limestone with the post-crushed limestone, because there's some open faces on wrap. So we blended those together and we matched the grayscale analysis. And that we tried to do two things. We tried to mimic approximately the same amount of material that was coated with material that was open. Because then when you actually start mixing the asphalt emulsion in during the mix design process, some of that asphalt emulsion is coating an existing coated surface, but some is coating a fresh surface. And those are two very different mechanisms. Did that make sense?
Yeah.
Okay. And what was the second question? I've already forgot.
The second question. Once you have provided this matrix, workability, compatibility, how do you ensure they are met in the field?
So the question is, how do you make sure they're met in the field? I think that I see these more as being done before you go out in the field. So you take cores from the site that you're going to be doing CIR on, and then in the lab, you do your asphalt emulsion content, your water content, any sort of additive content. You do all of that to match the specifications, the metrics, and the compaction metrics in this, the direct shear test. And in theory, then that will ensure that you have good performance in the field. But we're just looking at the design portion before actually implementing it in the field.
Right. Well, let's thank Professor Braham for a very interesting presentation.
Thank you very much. Appreciate it.